you.
Thank you. So, hello everyone. We continue celebrating the International Day of Women in Statistics and Data Science. And in special, I welcome all of you to the Portuguese contributions to statistics and data science. In this session, we intend to pay tribute to two Portuguese statisticians who play an important role in their respective research areas and whose work has been recognized by their peers. The first speaker is Soraia. She is a junior statistician who has received the scientific award for her research from the Portuguese Statistical Society. So I think we can start because we are a little bit delayed. So Soraia, you can start. Welcome and thank you very much.
Okay, thank you. Thank you, Isabel, for the nice introduction, and thank you for the invitation to be here. It's a pleasure. I will share my screen. I tried to change the name here, but I could not, perhaps because the link, but okay.
Okay.
Okay. So are you seeing the screen?
Yes, yes. Yes.
Okay. Okay. So I'm going to talk about spatial data and spatial models. The title of my talk is "Spatial Data is Everywhere. How can we make use of it?" So why this is important? Well, everything occurs in a specific space and time, and nowadays, as we know, we can easily have access to the information with this spatial detailed information. So even when sometimes our main objective is indeed to it's a spatial objective. For instance, to understand the spatial distribution of an event or to identify covariates that better explain that spatial distribution, for instance. But even when the main objective is not spatial, if we have that information, I think sometimes can be we would waste the information that can be very relevant to improve the inference process. So that's why spatial statistics has generated significant attention in many areas, such as epidemiology, engineering, and environmental health, among many others. And here, sorry, okay, here before I start describing some spatial modeling approaches, it's very important to clarify what spatial data is, and talk about the different approaches for different kinds of data. And Cressy in 1991 has described spatial data as resulting from observations of this stochastic process, YS, whereas belongs to D, where D is possible a random set of D-dimensional real space. And he makes a clear distinction between three types of spatial data: areal data, spatial point patterns, and geostatistical data. And this distinction is very, very important. Here, I represented an example of each type of spatial data. On the left, we can see the representation of the criminality rate in Portugal by NUTS2 region in 2018. So it's clearly an example of areal data. On the middle, we have the spatial distribution of forest fires in Portugal in 2000. And in this case, we have a spatial point pattern here, and we are interested in understanding the spatial distribution of forest fires, for instance. We could also represent, for instance, the burned area in each point. But even in this way, it would be a spatial point pattern, in this case, a marked spatial point pattern. And on the right, we have an example of geostatistical data. In this case, we represented here the 13x density collected in a regular grid by the Portuguese Institute for the Atmosphere and Sea. So they use this regular grid to record the 13x density in each point. So here, our main objective is the observations in those points. And now I will talk a bit about what are the methodologies more adequate for each one of these types. I will start talking about aerial data models. And in this case, the spatial dependence here can be considered through random effects, taking into account the spatial structure of the neighborhood. But sometimes this inclusion of structure random effects, especially when the likelihood is not normal, the model can become complex and the computational time can be very high. So here the methods that we proposed, or I will talk about, they are in a hierarchical Bayesian approach. That is one of the most effective ways indeed of to handle these issues. And in this approach using a hierarchical Bayesian modeling, the structure of a generalized linear model can be specified in these three levels. At first, we specify the distribution for the data conditional to the parameter of interest. Then we specify the relation between the parameter of interest and some hyperparameters, and we can include, for instance, spatial covariates and random effects, and then we specify prior distribution for the hyperparameters. Okay, so to show an example of an application of an aerial data model, I will show here a model that we proposed in the context of official statistics. It was a joint work with Perry Turkman and Luis Correia, where the main objective was to estimate unemployment numbers in small areas, such as NUTS3 regions in mainland Portugal. To give you some context, here we have the representation of the NUTS level in Portugal and also the municipalities. And currently, the Portuguese National Statistical Institute publish estimates for unemployment numbers for NUTS2 regions, and they are interested in find a method that allows to obtain estimates with a good precision, with an accuracy that is reasonable for official statistics in small domains such as NUTS3 and municipalities. So we proposed using spatial models, taking into account the spatial dependence here to improve the precision of these estimates in small areas. Here is the hierarchical model that we proposed in this case, where JT represents the number of unemployed people in region J and time T, in this case the quarter T, and we assumed a Poisson distribution for this total number of unemployed, where the intensity, the mu, is given by this relation where we include spatial covariates temporal covariates, spatial temporal covariates, and also structured spatial effects and structured temporal effects. So for the spatial structured effects, we assumed an intrinsic conditional autoregressive model that we will describe in the next slide. And for the temporal random effects, we assumed an autoregressive model, so taking into account the dependence between the quarters. For the hyperparameters, we assumed non-informative prior distributions. And this model is, and also an offset term here, this model is general and can be applied in many other contexts. So the intrinsic conditional autoregressive process is given by this specification. So where we take into account the spatial structure of the neighborhood, and here the specification of the autoregressive model to take into account the dependence between the quarters. Some curiosity here with the results of the coefficients of variation of the estimates using the direct method, that is the currently method used by the Portuguese National Statistical Institute, and the traditional methods used in small area estimation, and then the hierarchical model that we propose, taking into account the spatial correlation here. So indeed, we could improve with these spatial models the precision in these areas. But now imagine that we have not only the data aggregated in these areas, but we have more than this. Imagine that now we have the locations of the individuals in the sample of the labor force survey, and we don't want to waste information. We want to use that information. So here we propose with this information on hence we propose to use a spatial point process approach to deal with, to analyze these spatial point patterns. So Deagle in 2003 defines a spatial point pattern as a set of locations clearly distributed within a designated region and presumed to have been generated by some form of stochastic mechanism. So we can look at these locations of the individuals in the sample of the labor force survey as a realization of a spatial point process. And here the main objective is to understand the spatial structure of these patterns and to make inference, in this case of the unemployment, to make inference in the numbers of unemployed people. In general, a pattern can be classified as regular, random, or aggregated, and this is also very important to choose the model that would fit in our problem. So the most basic model for point process modeling is the Poisson process, as we all know, and we can divide these Poisson processes in two groups: the homogeneous Poisson processes and the inhomogeneous Poisson processes. The homogeneous Poisson process has two properties. First, the density of points is constant, and second, the locations are independent from each other. In the inhomogeneous Poisson process, the intensity function is not constant, it's a spatially varying function. And in particular, in the Cox processes, this is a particular case of inhomogeneous Poisson processes. In this case, the intensity is stochastic, and we will focus on these processes where we can assume the intensity as stochastic and to incorporate, for instance, spatial covariates and to make inference on that. In particular, we will focus on the low Gaussian Cox processes. And a low Gaussian Cox process is a Cox process with an intensity function given by this expression here, where Z is a Gaussian random field. So an alternative version, and we will, based on this, is to incorporate here the spatial covariates, as we can see. And here the beta 0 and beta are the regression coefficients, and XS are the spatial covariates, as okay. One example of this application, again in official statistics with this data, where we have the location now of the residential buildings of the sample of labor force survey in a specific quarter, and in each location we have also the information about the number of unemployed people. So here, to model this type of data, we suggest looking at the sample survey as a realization of a spatial point process together with the associated marks, namely, in this case, the number of unemployed people in each residential unit. So to model this process, we suggest a marked log Gaussian Cox process model, and the inference was made using the integrated nested Laplace approximation approach. Again, in a hierarchical Bayesian perspective. So we use this INLA approach, that is an alternative method proposed by Ru et al. In 2009. It's an alternative method to the MCMC methods, and it's very efficient. So allows the user to approximate the posterior distribution of interest. So here we use this approach. The hierarchical, we can see here the hierarchical structure of this model, where we are modeling jointly the locations of the residential buildings in the sample of the labor force survey, together with the attached marks that are the number of unemployed people in each location, and we assume a Poisson distribution for this, where the intensity of the point process is related with an offset term and this W that represents a Gaussian Markov random field. And the intensity for the marks are modeled through this expression here, where we incorporate spatial covariates and also the same Gaussian Markov random field. So the two processes are sharing a Gaussian Markov random field. So they are conditionally independent. If you have curiosity about the estimates that we obtain using this method, here we can see the unemployment estimates at kilometer square level. And here the coefficients of variation of the estimates obtained at municipality level in comparison with traditional methods in small area estimation and the direct method. But imagine now that we have more than, imagine now that we have more than this information, that we have now not only the locations of the residential buildings in the sample, but that we have access to all locations in the population. So now the locations are not random, the locations are fixed, and we are interested in modeling only the number of unemployed people in each residential building. So now this is a geostatistics, we have geostatistical data, and the problem is a problem of geostatistics, because we want in this case to make prediction of a variable of interest over a domain in the residential buildings that are not in the sample, based on the values observed at a limited number of points. So because here we have all locations of residential buildings, but we only know the number of unemployed people in each residential building in the buildings that belong to the sample of the labor force survey. So this is a geostatistics problem. The most classical approach for spatial prediction is kriging, but using this approach, if the number of observations is large, the modeling approach involving the spatial covariance can be time-consuming and unstable. So we suggest using the stochastic partial differential equation approach here to have this to solve these problems here. We have also an example of an application of these geostatistical models, again, in this context of official statistics. Here is the hierarchical structure of this model in this case. So we are interested only in the number of unemployed people in each residential building and time t. Here we made an extension for the spatial temporal setting. So we are considering a Gaussian Markov random field to take into account the spatial dependence and the temporal dependence simultaneously. Here we have the results of the estimates of total unemployed by nodes 3 using this approach in comparison with the other approaches, and the respective coefficient of variation of the estimates. And I think I still have some minutes, not much, I guess. And another example, just not to talk about only about official statistics, I have here another example of an application of the spatial models and extremes in this case in the context of ecology. In this work that it's still ongoing work, our data is the data that I presented at the beginning of the presentation. The Sardinex's density recorded at locations at regular grids, and these data were recorded by IPMA, the Portuguese Institute for the Atmosphere and the Sea. But here we have a challenge, that is we have many zeros in the observations and also extreme values. So we are interested in use a geostatistical approach here, but we think we need a mixture, and we are proposing to use a mixture between 3 distributions to take into account the extra zeros. So we could use a Bernoulli and then a gamma to model the central part of the distribution for the Sardinex's density, and then a generalized Pareto distribution for the extremes. But this is using the INLA approach, the integrated Nessel approximation. We have here some challenge because now our distribution is not unimodal. We have more than one mode here, and it's been a challenge that we are trying to solve using MCMC and INLA. So we are interested here. The main objective is to make spatial prediction in locations that were not observed, and also to identify the environmental variables that better explain the spatial distribution of this Sardinex's density. But as I said, it's still ongoing work. And to finish, I finish with this sentence of Tobler in 1970, where he says, "I invoke the first law of geography. Everything is related to everything else, but near things are more related than distant things." And that's thank you.
Thank you very much. Thank you very much, Soraia.
Thank you for,
and especially for the practical applications that you have presented of the spatial statistics. And now I would start with asking the audience if anyone wants to put any question or make any comment, because we have time for 1 or 2 brief questions. No?
So I wonder what this last example is a work in progress. Yes, work is
Yes.
Is a working progress. So can you tell me what do you expect to apply here, just in a very brief way, or what will be
Yes,
the greatest challenges of this new application?
Yes. So indeed, here with this mixture of these three distributions, the Bernoulli, GAM, and GPD, we have some difficulties using the INLA approach because we in this case we have not only one mode. So we are trying to use an approach that was proposed by Virgílio Gomes Rubio and also Verdú, a book that is available online about how to solve this problem. And the methodology that they propose is based on Metropolis Hastings algorithm within INLA. So try to combine these two very important approaches for the inference, MCMC and INLA, together to solve this issue. But it has been a challenge to do that indeed.
So a lot of computational work, I think.
Yes.
Okay, thank you once more, Soraia. So now let's move to the next speaker. The second speaker is Maria Eduarda Silva, and she is the former president of the Portuguese Statistical Society. So I won't say anything more about Maria Eduarda because I think it's better to listen to her instead of saying anything more. So she will talk about time series analysis and related with complex networks and other challenges.
Okay, thank you very much for your introduction, Isabel. But I can't share my screen if Soraia won't let me.
Yes, she has to move to remove the screen. Yes?
Okay, thank you.
Okay.
Okay, thank you very much. Thank you very much for the invitation. Thank you very much for the kind presentation. And thank you for being able to deliver this talk today here. So I'm talking a little bit about time series. And I will, sorry, I am so sorry, it's not this presentation.
I can say that Maria Eduarda is an associate professor with habilitation at the Faculty of Economics at the University of Porto, and currently she is the president of the Pedagogical Council and director of the Master in Data Analysis. Concerning Soraia, she is a researcher at Center for Statistics and Applications, and she's an invited assistant professor at Faculty of Sciences at the University of Lisbon. So one is in the north and the other in the center or south, I don't know, of the country. So.
Okay, I'm so sorry that I was giving classes.
Okay, continue.
Okay, thank you once again. So today I'm talking a little bit about time series. So I will talk about some issues that I have been working on during my career, and then I will focus on a new approach. So everyone knows that time series are data indexed in time, and the intrinsic ordering of the data and the serial correlation presents several challenges, and I like to introduce this subject to my students with this little example, because even simplest statistic that we have, which I consider to be the sample mean, the properties of sample mean are affected by the serial correlation in time series. So we have here 5,000 sample means from IID observations, and here we have 5,000 sample means from a time series with a small leg 1 correlation, and when we increase the serial correlation, then the sample means present much more variability. And therefore, we have to devise a long time, last 50, 70 years, several methods have been developed to deal with these challenges in time series, and I would like just to mention a few. And I've been working, and with Isabel, with the time series of counts. So we have correlated count data. We need special models for this data, since the traditional models for time series cannot capture the integer value characteristic of the data. Therefore, I worked with integer valued autoregressive models, estimation, finding outliers, and also in the multivariate case, and proposing a model for bivariate binomial data. So these are some of the publications. Another special important issue, it's very important, it's irregularly spaced time series, because one of our assumptions is that our time series time is regularly spaced, so every year, every month, every hour, so on. But in some examples, we have that the time of the observations are in fact irregular, but more than irregular, they can even be dependent on the value that we are observing. So I have worked a little bit with this with some colleagues, and there were some publications. Another interesting issue is related to limited dependent variables, and in particular time series and censoring. Under censoring, what is this censoring? The easiest example are measuring devices that sometimes have limits, so we know we cannot observe above a certain limit or below a certain limit. So these limits are imposed by device constraints, and when we have time series in this under this observed data under these constraints, how to model, how to infer, how to forecast. So there are some work both with continuous variables as well as integer valued variables, and with Isabel. More recently, I have focused on another theme, which is using other data to now cast macroeconomic variables, which is this other data, data that comes from online activities. In particular, we are now casting, I and a student now casting the monthly unemployment in Portugal using Google Trends. The data is mixed frequency, meaning that the unemployment is monthly, but Google Trends that we are using is daily data. Then there is this feature approach, but I will talk about it a little bit later. So just to finish, I have also worked with particular areas, and in particular cardiovascular and respiratory time series, modeling long-range dependence in univariate and multivariate approaches with data from the hospitals, okay, real data, and also predicting the dosage of the drugs during surgical procedures for automatic control of anesthesia. And also did some sea-level studies.
Eduarda, can I ask you a thing? Can you move or change to a present mode? Because
yes, it is not.
I think no, it does. It is.
Oh,
There's a difference.
sorry, because I have two screens and I see present mode.
Okay, this.
Oh, okay. So I'll change here.
It will be nicer. Thank you.
I'm sorry that this is not going so smoothly as I expected after trying several times.
It happens. Don't worry. It happens to everyone.
No worries. We're happy to have you.
Yes, because we are seeing very well, but it will be better.
No, no.
Okay.
Okay. So
Okay.
I moved to
Okay.
a smaller screen.
Perfect.
So-
Okay, it's perfect.
Okay, I'm so
Yeah.
sorry.
Okay. You can continue. It's okay.
Okay, so now I'm just going to to present another approach for time series analysis, and this is via complex networks. This is joint work with my colleagues from Faculty of Science. Vanessa was a student, PhD student, and the paper is the presentation is based on this paper.
Mhm.
Okay, so what is the motivation for this? Well, we all are aware that technological developments led to large amounts of data, and in particular, large amounts of time series, and it is currently in some business, for example, in retail or in energy, you have hundreds and even thousands of time series to analyze, to forecast. But start with a smaller problem. I want to look at the series, at the data. And if I have too much data, I can't look at all those time series. And Heinemann recognized this problem long ago. In 2006, he proposed, based or inspired by the work of Tuckey, to use features to characterize the time series. What are features in time series? Features for statisticians are statistics, and the statistics for machine learning are features. So I'm going to use this term features because Heinemann uses this term as well. So it's like correlation, the strength of trend, seasonality, whether there are unit roots, periodicity, entropy, and there are quite a number of these features that he has developed over time. And he has been using them quite successfully to represent the hundreds, thousands of time series in the feature space, and then find anomalous time series or find the best forecasting model, clustering, and so on. So our approach is a little bit the same in the sense that we are going to get to find features, but we are using complex networks. So the outline, so I will start by introducing a little bit about network science, a little bit. And then from how do I get from the time series to the networks? How do I represent a time series as a network? Then the set of features that we are considering, and one or two examples. Okay. So what are these complex networks? Complex networks are representations of the complex systems that are around us in real life. And they have been quite successful in representing and studying different complex systems. So what do we have? We have the system which has some elements, and we represent the elements in the nodes of the graph, of a graph, and then link the nodes according to the relationships between the elements. These links, the edges of the graph, may be directed or not directed, or may be weighted, like in here, or not weighted. And then the graph is mathematically represented as a matrix. And I think it's quite self-explanatory. Of course, people from computer science, there are other representations, but I keep to the matrix. Okay. So network science, which is the science that studies these complex networks, developed several topological features to characterize the networks. And these are only a few examples, because there are quite a lot of topological features. The first, which is one of the most important, regards node centrality and the importance of a node in the network, and that importance is measured by the number of links that the node has to other nodes, and that is called the degree. And if each node has a degree, that is, we can have an average degree for the whole graph. Then we can another measure is related to the distances that you have to go through in the graph to get from one node to another node. These are path lengths. So how many edges you need to get from one node to the other node. Of course, this measure, in a sense, represents the dimension of the graph. Then you have clustering properties, and they are measured. One of the measures is related to how the neighbors of a node are connected among themselves, and it is the clustering coefficient. And finally, just the last example relates to communities, and these are related to the connections between sets of nodes, and these sets of nodes are communities. Okay, so what we have is that in around 2006, 2008, some people, researchers from physics and dynamical systems started representing time series as complex networks. And we did find that literature and decided to look a little bit further into the problem. Okay, so how do I go from time series to the network? How do I represent a time series as a network? We use mapping, so we map the time series into the network, and there are three concepts. I will focus on only two of them. So the three concepts are visibility, transition probability, and proximity. Okay, let's start with what we call visibility mappings. Right. These visibility mappings depend on geometrical concepts. Okay, so here we regard our time series, our data, as pairs t, y at time t. And the t, the time, is mapped into the nodes. Okay, so there are as many nodes as there are times. Okay, then there are two concepts of visibility. I will start with the horizontal visibility. We define that y at time t and let's say node t, let's use node I at time I and node at time j are connected naturally, horizontally connected, and it's these blue lines. If for all t's between I and j, the y at those t's is smaller than the y's at our variables, our observations at times I and j. So for example, 6 is, well, the neighbors time t plus 1 and time t minus 1 is always connected to time t. Then here, node 6 will be connected to node 8 and will be connected to node 9 and will not be connected to node 10 because 10 is here, okay, nor 11, but will be connected to node 12. Okay, so this is the horizontal visibility. We can put weights on these edges. Then we have the other concept, which is called the natural visibility. And in this case, we define a straight line between the two data points, I, y at time I, and j, y at time j. And we consider that the nodes y and j are connected if for all times between I and j, y at those times keeps below this segment line. So here, time 2 is connected once again to time 3 and 1, of course, because they are just the neighbors. But then we have here 2 to 4, 2 to 6, but not 2 to 5, because the straight line that is here at time 4, the value y at time 4 would be over the straight line.
Eduarda, okay. You just have 3 or 4 minutes at maximum.
Oh,
yes.
I can do this.
Okay, sorry.
Sorry.
They're automatic over the wall, so that's the
okay.
problem.
So there is the. I'm so sorry. There is the other mapping, which is based on quantiles, and we divide our data on, in this case, in 4 quantiles, and compute the transition between quantiles. So I'll go through to the example. Okay. Mm-hmm. After getting the graphs, we calculate the topological features of the graphs. In this case, we have 15 different features. So we have our time series. We map them into the graphs and calculate the topological features of the graphs. Okay. We have evaluated with empirical synthetic data. And we have here an example related to the first plot that I have here, many time series. There are 9 products in 109 regions in Brazil, monthly data from 2002 to 2018. And this is an example of each product. So markets, textile, furniture, and so on. And when we do this representation, extract these features and represent the 109 109 times 9 products time series in the space of the features. We see that we get some products that stand out, like energy is over there, X are over here, and then we have gasoline and cattle production over here. What I want to call your attention is that we can identify here some here in the X, for example, some of these time series are a little bit different from the great majority, which is over there. And let's look at these different time series. So that represents the time series in the center of all the 109 time series. And these are what we call the layered because they are a little bit distant. And we see that, in fact, there seems to be some reason for the features to stand out this. Also, with the cattle, it's the same. So these are the most weird the time series that are a little bit away from the main group of time series. Also, we did some clustering with this data set and set of features from the networks suggest 4 clusters, and X and energy make 2 clusters, then these 2 another cluster, and then the remaining in the 4th cluster. If we look if we look at the silhouette of the clustering procedure, we see that the groups are quite except the X. These are the X. The X have very different, as we have seen, time series, but the other groups seem to be quite tight. And this clustering is, in my view, much more coherent than the clustering obtained using other features that are available in the literature. This is called Catch-22. This is called TS features. Okay, so,
unfortunately, I think we have to finish.
I'm so sorry. I'm so sorry. Okay.
Okay, I'm sorry. I close this session thanking the participation of all of you, special speakers, and a special thanks to the session organizers, Ligia, Wanda, and Clara. Thank you, and I'm so sorry, Eduarda, but that's the rules.
It's my fault. It's my fault. Okay. Next year I will finish.
Okay.
Thank you.
Bye-bye. Thank you.
Bye. Bye-bye.